मैंने एक ले लिया। भैया देखे इसमें है भैया अच्छा चेक पे सिग्नेचर होता है तो चेक पे
Hello, good afternoon, sir. Is this Madhu?
Good afternoon.
Sir, good afternoon, sir.
Good afternoon. और कैसे हैं आप?
सर बढ़िया।
अच्छा।
सर कितने स्टूडेंट अच्छा पार्टिसिपेंट 77?
Right now I can see 77 participants are there.
Okay, okay, okay.
और
Sir, what will be the mode of instruction? Bilanguage or only?
Bilanguage.
Bilanguage.
Hindi or English. Hindi or English.
Okay.
The purpose is that they can understand the things.
Okay. Okay.
They can understand. This may be very new for someone. ANSYS. And we have already purchased the multi-physics ANSYS. And with the electrical, mechanical, civil, all students and faculty can work on this.
I have generalized my lecture for all participants, but it is a more mechanical specific actually.
Definitely, this session is only for mechanical, and you can also see that if you other participants, if they need further your support in terms of this online lecture, so please come forward and help them.
Sure, sir.
As per your convenience. Okay.
Sure,
sir. So shall we start?
Madhurima, yes, you can start.
Okay, sir.
Yeah.
A very hearty good afternoon to one and all present here. Welcome you all. First of all, I would like to thank RGPV Bhopal for giving me the opportunity to host this great event. First of all, I would like to thank RGPV Bhopal for giving me the opportunity to host this great one-day online workshop on Introduction to Engineering Simulation using ANSYS. I, Madhurima Sharma, welcome once again each and everyone on behalf of RGPB TechUp 3 Bhopal. I feel grateful to welcome our respected Professor S.C. Chaube sir, the coordinator TechUp 3 RGPB Bhopal. Now I welcome our expert Dr. B. Rawal sir, Professor and Head of Biomedical Engineering Department, SGSITS, Indore. Sir has done his BTech from MITS Gwalior and MTech from NIT Allahabad, PhD from IIT Delhi. Now may I request respected Professor S.C. Chaube sir, Coordinator TechUp 3 RGPV Bhopal to address us. Sir, please, over to you.
Thank you, Madhurima. Professor B.R. Rawal, Professor and Head Biomedical Engineering Department, SGSITS Indore. All participants who are present here on this virtual platform to listen our expert, Dr. Rawal. In fact, I was very much interested that the students of RGP affiliated institutions must be aware of some of the software which are very useful, like ANSYS, CATIA. And for that purpose, TechUp 3, RGP TechUp 3 developed a research hub, and where this university has procured multi-physics bundle of ANSYS, CATIA, and many other softwares. And where, in fact, we are very much fortunate to invite Professor Rawal that time to prepare the specification of ANSYS and CATIA. He acted as an expert, and on his advice, the specification was finalized. Then it was the right time to again invite him and to share his experience. He had a vast experience of teaching. He had been at IIT Delhi, at different institutions. He had been as either a research scholar or a student, and right now serving at a good institutions as SGSITS in Indore. Just, I would like to request all the students and faculty members who are here that after this seminar, after this webinar, if you are really willing to work on this ANSYS, TechUp 3 will provide all kinds of platform support from experts, and let them to start ANSYS. Why I am saying it's the right time, when we are talking, and our Honorable Vice Chancellor, our Honorable Prime Minister is talking about the Atmanirbhar Bharat, Make India, then this kind of software, because this is the place where our mechanical engineering students and faculty can survive. When you're talking about the product design, even everything you can see that every small operation is based on IT. But you know, this product design is everywhere. Even if you are driving a car, every operation of the car can be automized using this ICT and other sensors, IoT. But at least the entire design of the body, design of the engine, it is based on the product design. And here I can see that they have got a vast scope. Equally, we have to compete globally. That is where we are here to learn. And definitely, I am very much sure that what you learn today, and this will be a milestone in your career and all the mechanical engineering. So once again, I thank to Professor Rawal to be with us and to share his experience. I also thank to all participants and TechUp team to organize these programs and be here with Professor Rawal. Thank you. Thank you very much.
Thank you, Professor Chaube sir. And thank you for invitation. Now I am going to present my
Thank you, sir. Now I invite our expert of the session, Dr. B. Rawal, sir. Sir will take session on Introduction to Engineering Simulation using ANSYS. Sir, please, over to you.
Okay. Okay, it is visible to all,
Yes, sir, it's visible.
and I am audible to all.
Yeah, you are audible. Please.
Okay. Okay, I am going to start now. The topic of my lecture is Introduction to Engineering Simulation using ANSYS. Basically, learning of ANSYS divided into three parts. At the first one is at the beginning level, then intermediate, then advanced level. In my today's lecture, I will talk about the beginning level. Okay. So this is the plan for today. First 30 lecture, I will talk about the FEM, fundamentals of FEM, in which I will cover the fundamental concept, analysis procedure, where we make mistakes, and how we maintain the accuracy of analysis. And second part, this is the introduction to ANSYS. Basically, I will discuss ANSYS workbench, and this is by a video lecture. Step by step procedure is there that will be covered in a video lecture. Then finally, in third part, problem solving on ANSYS workbench. This consists of 60 minutes. So here I am talking about what is FEA. FEA, or the full form is finite element analysis, or you can say it's a FEM, finite element method. Basically, the idea of doing this analysis to divide complex object into manageable pieces. See, this is a circle. If you want to find out the area of this circle, how you can find out? Suppose we are having the formula of finding this area, but we suppose we don't know the formula of how to find out the area. Then how we can find out? If we know the area of triangle, so we divide this circle into uh, uh, this triangles. So by counting these triangles, by fitting this triangle, and we have an area of this triangle. So by counting this, we can find out the area, and this is an approximate area. It's not an exact area. And how we approach this to exact solution, exact area, by increasing the number of triangles, fitting triangles in this circle. So in same way, if we want to find out the exact solution of any geometry, then we have to increase the number of nodes. Now again, it's a numerical solution for field problem of and it's again cuts into a several element like this. It is showing this. We have divided into manageable pieces. And about the compatibility of this analysis, first we have to check that it is a continuum, means the geometry is continuous, and we this is a infinite, and when we divide into a number of pieces, it become a finite. So that's why it is known as a finite element method, because it's the number the elements are finite in this case. Now, what is again, FEA methods give an approximate solution. It will not give an exact solution. Mainly used generally, there are three. We analyze the engineering problem in a three way. First is analytical method. and second is numerical method, and third by experiment method. Analytical methods we do for some simpler geometry, and based on the mechanics of solid fundamentals, we solve those geometries for strain, for deformation, stress, and strain. Here, FEM is considered to be a numerical solution, and in this solution, we are not getting exact solution, but it's a approximate solution. So it's rather than analytical solution, it's a numerical solution. First, it was applied for finding out stress and strain for a engineering component under the load. For development of FE, we divide complex geometry into simpler element, and by characterizing that element, we form a large number of equations, and those equations, for solving those equations, there are large, huge number of those equations. For those equations, we generally need that cannot be solved by manual. So we need computers. So with the advent of these good computing machines, personal computer workstations, now we are using these computers with the help of digital for display. So we are using computers basically for solving FE problems. FE method can be applied a wide range of material properties. Sometimes when we are considering analytical method, we face when there is non-linearity in material behavior, and sometimes when the geometry is complex. So we have a limitation for analytical method, but in a numerical method, or basically by a finite element method, we can solve, we can over this limitation, and we can solve for nonlinear problem and complex geometry. Many comprehensive general purpose FE systems are now available. Many we will discuss later about these softwares. They are more specialized packages for particular application. Depending on the type of and complexity of analysis, large number analysis may benefit for multiple processes. We have different types of analysis. FEA can be divided into 1D. The engineering problems we can solve by considering it a 1D problem, 2D problem, and 3D problem. So we can do structural and stress analysis, dynamics and vibrational and heat conduction, fluid mechanics, electrostatic analysis. Not these are the few. We can do more analysis. Now, fundamental concept. We do mathematical. Basically, we do mathematical modeling. Mathematical modeling is nothing but formation of governing equation. What is governing equation? It is nothing but the relation between input and output. Suppose if we are considering about the structural problem, what are the inputs? What are the inputs? Material properties, geometrical properties are the input properties, and what are the output properties? Means unknowns are there. Generally, in structural problems, we want to know the deformation. So it is unknown. So by maintaining the physics of for engineering problem, we have to form a relationship between unknown these input and output parameters, and this is basically a differential equation as shown in this differential equation. So this is a governing equation, and we convert these differential equation into linear equations. And we can solve this by, for solving a finite element problem, we have to have a boundary condition also. So by putting a boundary condition, we can solve this. So for solving a finite element problem, we have to have boundary condition. Without boundary condition, we cannot solve. This is the example of vertical machining center. This, if you know this, that this is the geometry of this machine is very complex in nature, and we want to know the deformation here, the deformation and thermal behavior of this machine. So what we do, we divide this whole geometry into a number of pieces that is known as elements, and this form a governing equation, and by putting this boundary condition, so finally the equation, the form of equation of is into this k, u and f. This is the material property, this is a known, actually known property. This is unknown, this is the field variable, generally deformation, and this is the force, this is the action. So like this, again, this is a property, this is a known, and this is the behavior unknown. This is the unknown physical field parameter, and this is the action, what will happen due to the, like in a structural problem we consider here, the action is considered to be the force. So here, this is the u, behavior is the unknown, and how we can find out this unknown behavior? By solving these equations. So for other analysis, this is elastic analysis. Elastic means structural analysis. Here the property is given is stiffness, and the behavior, the things that we find out is displacement, and the action is a force. For thermal analysis, property is given is conductivity, and behavior is temperature, and action is heat source. And for solving a fluid problem, basically we use CFD for this solution. But in ANSYS also we can solve fluid problem related to fluid. And here the property is given viscosity, and we are interested to find out the velocity. And here the action is body force. For electrostatic analysis, the property is dielectric permittivity, and here behavior for unknown, it is electric potential, and for action here the charge is there. So here, as I told you earlier, this whole machine, we have to make a CAD model of this, and this CAD model is divided into non-manageable pieces. These are known as element, and these element is consist of various nodes. These are the nodes. These nodes, the function of these nodes is to when we assemble these elements, these form a connecting link. So the various elements are connected at the nodes only. Again, we characterize first the different element. After characterization, we form an assembly of these elements, and then that assembly is known as global matrix. Global assemble, and then its global assembly is generally based on the behavior of individual element. Now, how we solve this is the now a global, when we have global matrix. If we talk about the element level, this become the element stiffness matrix. Once it become a global matrix by assembly. Hello, any question? This become global matrix, and by putting the boundary condition, we actually solve. The solution part is caring of by this computer. So here the user can give some input in this phase and interpret the result in this phase. So the participation of user comes to this part and this part. So in summary, basically we divide the whole complex geometry into manageable pieces, and that pieces should be characterized for we have to characterize for the behavior of that element. So basically generally done by polynomial interpolation. For suppose for this is for like finding out deformation. Suppose this is a now I am giving the example how we characterize this element. This is the again this is the equation for FEM. This is the property. This is known. This is unknown. We want to know the behavior of that element, and this is the action. This is generally force. External. It may be external force. So take the example. This is a spring. Here the action is this is force applied load, and here the known thing is the spring stiffness, and we want to know the displacement. So here we do mathematical modeling for this. Basically, we do to maintain the physics of that problem. We have to take some scientific law, scientific theory. So here we are taking the equilibrium of forces. So suppose this is the element whose node is 1 and 2. This is a spring element whose stiffness is K given by K. Here is the nodal force. F1 is the nodal force that is applied to the node 1, and this is the F2 is the nodal force which is applied at the node 2. Here this is U1 is the nodal displacement at the node 1, and this is the and U2 is this is the nodal deformation at node 2. So at so here the deformation is comes to U2 minus U1, and this is a equilibrium of forces. When equilibrium of forces, the relations between this deformation and applied load is F given to K delta. For equilibrium, the F1 and F2 is 0. So this become F equal to minus F2. So as per this equation, we form a equation. F1 is minus K, U2 delta become U2 minus U1. Why it is minus? Why it is minus? Because suppose now we're talking about the node 1. We fix this node 2, and if we apply a force in this direction, what is happening? There is a reduction in length of this element. So this is a compressive. Actually, there is a compression is there. So for compression, we put the minus sign, and suppose we want to analyze this nodal force at node 2. So we fix this node 1. Now we apply this force. So this is a tension type. It elongates the length of this. So it is positive. Now this becomes the simultaneous equations. So we can write in a matrix form. This is K minus K, and U minus this is U the deformation at node 1, and this is the deformation node at node 2. This is the nodal forces F1 and F2. So we can this become the elemental stiffness matrix, and this is in form of this K, U, and F. So this is for this for only the one element. It can when it consists of more element, you can assemble by this and form a global matrix, and by applying a boundary condition, you can solve this. About the brief history about the FEM, first it is coined by Clark in 1960. It was used to find out the stresses, fluid flow behavior, and heat transfer in other areas. First book published by Jankovic and Chang, published in 1967. And then finally, the lots of FEM softwares are there, which was come into existence in 1970. Now the advantage of FEM, we can solve very complex geometry easily. We can handle a variety of engineering problems like solid mechanics problem, dynamics, heat transfer problem, fluid, and related to electrostatic problems. Can handle complex restraints where the non-linearity in geometry is there, non-linearity in material is there. So we can, these are the main advantages. This is an approximate solution. It nowadays it become a vital tool to analyze engineering problem. Disadvantage, it's a closed form solution. So once you committed a mistake, it propagate and become an inherent error, and you cannot debug this. So if you make a mistake, it become a fatal. This is the great advantage of this is a main great advantage disadvantage of FEM, that it's a approximate solution. Now this is the flow chart. This is the workflow diagram, how you accomplish any analysis on any commercial software. So that is in between processes generally computer solving the simultaneous equations. And basically this is the algorithm, the solvers are there, they solving for unknowns. Basically Gauss elimination methods generally are used to solve those simultaneous equations. There are huge number of so before solving, uh, there is the steps come that is known as pre-processing. Basically these are the inputs that can be given by user, and after solving this, the result can be interpreted in a process. That process is known as post processes, and here the user again interpret the result. So in pre-processing, generally what a user can do, first he has to select analysis type, whether it is a structural, model analysis, transient type, buckling. This is basically to maintain the physics of engineering problem. So to maintain the physics, we cannot go beyond the physics. So otherwise, if we go the beyond of the physics, then result we will getting are not reliable. So we have to maintain the physics. So first we have to analyze the type of analysis. Then we analyze the type of element. Basically for 2D element, it is linear or quadratic. 3D element, it can be tetrahedron, hexahedron, and truss element. This is a 1D element, cell element, plate element. This is for surface 2D element. And you have to give material properties also, and Young's modular Poisson's ratio, density, heat coefficient, all these things. In you have to make a nodes. You have to manage number of nodes also. You have to make a connectivity. You do assembly, and then finally in pre-processing you have to apply boundary conditions, where you have to give support. We have where you have to give boundary conditions like this. Then processes, it is solved by computer. And then post processing, generally you have to interpret the result. It may be for displacement, stage, strain, natural frequency. For model updating, if you are talking about then you have to analyze the natural frequency, temperature, time history, like this. Responsibility of user, because it is giving colorful contour plots. It looks very fancy, but you have to be careful that pre-processing should be proper. If you committed mistake in pre-processing, then result you are getting will not be reliable and not be correct. So it's like if you put garbage inside, you will get garbage out, garbage in, garbage out. So be careful, and it's a responsibility of user to take care of all these things like boundary condition, input conditions, all these things. uh, how we characterize the element. Suppose this is a domain, it's a complex in nature. We are dividing this complex geometry into a manageable pieces that are known as element. Now, how we characterize the behavior of that element? Suppose if we are talking to know the deformation inside this, so it may be two deformation, it may be like this. So we can assume it may be linear. So we can assume like this. Its equation like u become a plus bx, a plus bx. Here the it's linear for linear the deformation. Here quadratic, and it's a cubic element. If we are increasing the order of polynomial, means we are approaching to the solution. Similar way, if we talking about the solving FEM problem on commercial software, if we increase the number of element, then we are approaching that is known as mass convergence. So before going to final solution, before going to solution, you have to do mass convergence also. This is a basically interpolation functions and known as a safe function. Mistake by using by users, I already told about this. These are the commercial available FEM software. ANSYS, it's a general purpose which can be installed on PC and workstation, personal computer. Ideas, it's a CAE, computer aided engineering software. Nastran, it's also a general purpose software. Ditran, it's very good for nonlinear and dynamic analysis. Abacus, very popular commercial software mainly used by auto industries, and it is very good for nonlinear and dynamic analysis. Cosmos is again, it's a general purpose FEA software. Algor, it's good for it work on nicely on a PC and workstation. Petron, it is good for pre and post processing. Hypermath is a very popular software. It has good features for pre-processing and post-processing. And LS Dyna, it's a very good software for impact or crash analysis. Now, here I have finished the first part. Now I switch to second part, the introduction to workbench. Here I am, these are the various analysis type, fluid flow, harmonic, IC engine. You can design IC engine and you can analyze IC engine for structural and as well as thermal stresses, magnetostatic model updating for a response for natural frequency, model acoustic for generally noise level. You can vibrations like this, static, acoustic. So many are analysis are there, but here it's a YouTube video and very good video. YouTube flooded with lots of videos based on the ANSYS. You can learn ANSYS from those, but this is a very good as far as the introduction is concerned. So I am playing this.
Their elastic property. Starting ANSYS Workbench. So before we get started, let's go through a quick overview of what we'll be covering in this module. First, I'll be going over some of the prerequisites you'll need in order to continue with the course. I'll then briefly explain why we use ANSYS Workbench, and then I'll do a quick overview of the finite element method and how it applies to our problem. Finally, we'll start ANSYS Workbench, and then we'll go over the interface, the units, importing CAD files, and finally, the engineering data application, where you will define your materials for the analysis. Prerequisites. First, you'll need ANSYS version 17 already installed and configured, along with either a mechanical or structural license. If you don't know what any of these are, then you should please contact your ANSYS vendor for more information, as this course will not cover how to install ANSYS Workbench. Secondly, you'll need to have a good knowledge of the finite element theory, which means that you would have a solid engineering background, and you should be familiar with some of the governing finite element equations, such as stiffness times displacement equals force, as well as some basic knowledge of element types, such as the tetrahedron and hexahedron and their node counts. So why use ANSYS software? Well, ANSYS is a useful tool to solve problems with complicated geometries, loadings, and material properties where analytical or hand calculation solutions are difficult to obtain. In our problem, for example, we have a lifting lug design with a bolted connection and multiple fillet radiuses and somewhat complex geometries. So let's say we want to solve the stress in every area of the system and find the location of maximum stress. It would be possible, however, it would be much more time-consuming and less accurate when compared to the finite element method. So we also use ANSYS to ensure the design safety of our equipment. So we'll be able to answer some of the following important questions, such as at what load will my lifting lug fail, and where would the maximum stress occur in the system? And finally, it'll also be able to help us provide design insights and optimization, which could potentially save us material costs and increase the components factor of safety. So here's a quick finite element method workflow overview. One will start off with a physical model they would like to analyze. They will then take the model and convert it to a 3D CAD model and split the model into many elements, hence the name finite element. After applying loading and boundary conditions, we will then solve the model and obtain the results, which can include deformation, stress, and many other types of results. So in our case, the physical model is the lifting lug, and the FEM model will be the conversion of the real model into a 3D CAD model. And then after dividing the model into finite elements and applying the correct load and boundary conditions, we'll finally obtain our stress results, deformation, and other results. So what are we waiting for? Let's go ahead and start ANSYS Workbench. So once you open up ANSYS, you'll be presented with a Getting Started page with some useful tips on how to begin a project, as well as a link to some helpful tutorials. I'm just going to go ahead and uncheck this for now and click on OK, because I don't want this pop-up to keep on showing up every time I launch ANSYS. If you ever want to bring this page back up, you can always go ahead into the Tools, Options, and under the Project Management tab, you will see here the checkbox for Show Getting Started dialog. You can go ahead and check that, and then click on OK, and then every time you restart ANSYS, you'll always get that page back up again. So when you open up a new project in ANSYS Workbench, it opens to the Project tab, which is just one of many tabs that can be opened in Workbench, but it's the main workspace in which you'll build your analysis. Like all tabs, the Project tab is made up of different views that can be reconfigured according to the information we want to see. By default, the Project tab has the Toolbox view and the Project Schematic view. The Toolbox view contains the types of data you can add to the Project Schematic. The systems are divided into categories, which can be expanded or collapsed in order to show or hide the system in that category. The analysis systems are ready-made stencils that include all the individual components needed for a common analysis, such as the geometry, the mesh, the solver, and post-processor. The component systems are the individual building blocks for each stage of these analyses. So one could create their own analysis system by using these blocks. If you decide to create a custom system and would like to save it, it will be shown in the Custom Systems category right here. Finally, the Design Exploration category right here provides tools for optimizing the design and understanding the parametric response of the systems. Now, these toolboxes can also be customized to add or remove systems as needed in order to personalize your workspace. And if you don't see any systems here on the left, then you most likely have a licensing issue, and you should contact your ANSYS vendor for support. The mechanical or structural license that I mentioned before should give you access to the analysis system called static structural, which is the only system we'll be using for this course. So you don't have to worry about any other systems. Isn't that easy? Next, at the top of Workbench, you have the menu bar, which contains the file menu, where you can go ahead and create a new project, open a project, save a project, as well as archive, which is slightly different. This basically saves all the project files into one single file, which makes it easy to send over email. And then if you ever receive that, you can also go ahead and click on Restore Archive, which will expand this archive project, and we'll go ahead and open it that way. You have the View menu, where you can go ahead and reset your workspace in case you made some changes you didn't like. And you can also go ahead and turn on and off some views that you don't want to see. Like if we want to hide the toolbox, we can go ahead and click on this right now, and as you can see, the toolbox disappears. If we go ahead and click on it again, we see that it reappears. We have the Tools menu, which contains some license preferences as well as ANSYS options. We have the Units menu, where you can go ahead and change your units. The Extensions menu, where if you go on ANSYS.com, you can go ahead and download some extra extensions which can further enhance your ANSYS experience. The Jobs menu, where you can go ahead and launch a solve on a remote machine. And finally, you can click on the Help menu, and more specifically, the ANSYS Workbench Help, which contains all the documentation for ANSYS that you'll need to get started. At the bottom, we have the status bar, which shows ready and a green light. If this was red, this would mean that ANSYS is currently either loading an operation or maybe loading an analysis system. On the right here, we have some quick access tools to the remote job monitor, the progress, as well as the ANSYS messages, which is quite useful. So you can go ahead and check this box right now. So now that we've gone over the ANSYS interface, let's go ahead and start the project. So the first thing we're going to do is either double-click on the static structural analysis or click hold and drag it onto the project schematic and then let go. This will basically add the analysis system to the schematic. Now ANSYS will automatically ask you to name this analysis, so we're going to go ahead and type lifting lug, and then we're going to hit enter. Now, as you can see, the workflow is from top to bottom. And as each stage is complete, the icon on the right-hand side will change. Now, these icons are called cell states. So let me just give you a quick overview of each one of these cell states. So the first one is the hollow question mark called unfulfilled. This means that the required upstream data doesn't exist. So in this case, cell 4 is not updated and therefore doesn't exist, so cell 5 is unfulfilled. The second one is the green arrows called refresh required. This means that the upstream data has changed since the last refresh or update, so you may need to update this cell. The third one is the solid question mark, which means attention required. So it means all of the cell's inputs are current, however, you must take some kind of corrective action in order to proceed. The fourth one, which is the yellow lightning bolt, means an update is required. So you can go ahead and double click on the cell and click on update in order to update the cell. The green check mark means up to date. So this cell is completely up to date. And the green check mark with the yellow arrow means that the input changes are pending. So the cell is locally up to date, but may change when next updated as a result of changes made to the upstream cells. And here are some other cell states, which I will not be covering right now, but you can go ahead and find them in the help menu. So coming back to the project schematic, we can actually build the same analysis system using the component systems instead as an alternative workflow. So we can go ahead and individually create the system by, let's say, selecting the geometry and dragging it into the project schematic, and then going ahead and then dragging the mechanical model on top of the geometry in order to link it together to create the mechanical model. And then finally, we can go ahead and drop a static structural on cell number 4 to link all that together into the static structural. So this is basically another way of creating the same workflow. However, in this case, you can create individual blocks. So let's say we can start with the geometry and then create our mesh, but then let's say make a thermal analysis instead. So we can go ahead and drop that there. And then now you can see using the same geometry, we can run the static structural and thermal models side by side. So the square connector shows that the geometry created in this previous cell here is being shared with this cell over here. So any modifications to this one will be automatically updated in this cell. Now, if we add, let's say, a steady state thermal analysis and we drag it onto our schematic over here, and let's say we ran a static structural analysis and we want to use the results of this structural analysis as an input to our thermal state model, well, we can go ahead and click on, let's say, the solution and drag it into cell number 4, the model, and this will create a round connector. And the round connector means that the results of this analysis is being transferred as an input condition for the next analysis. So should you ever want to rename an analysis system, you can go ahead and click on the small down arrow on top of each system. And then this will bring up a small pop-up menu, and you can go ahead and click on the rename. And then here you can type in renamed part. And there you have it. And this menu actually also has a bunch of other features that you can do, such as update the analysis, create a copy of it, replace it with a different system, clear its generated data, delete it, see the properties, and even add a note. So we're just going to go ahead and now quickly delete all of these systems and click on OK when the pop-up menu comes. So we're going to delete the steady state thermal, we're going to delete the static structural, delete the mechanical model, and then finally we're going to delete the geometry. So now that all the components are deleted, let's go ahead and save the project. So we're going to go ahead and click on the File menu and click on the Save As button. Once here, we're just going to call this Lifting Lug Tutorial. And then click on the Save button right here. Now that our project is saved, I want to just go into more detail about the View Files tab. So let's click on the View and then click on Files to show the files. So this will enable you to identify the individual files on your disk for each stage of the project. The resulting table will cross-reference the directory and file names with the project cells. So as you can see, the Workbench project comprises of many files and directories on the disk. As mentioned before, if you need to archive the project or bundle it to send, use the Archive tool, which generates a single zip of the entire project. So let's go ahead and do that now and click on Save. When archiving, you can either choose whether to include the computed results file or not. Omitting these results file can greatly reduce the file size of the archive, which could make it small enough to even send over email. So let's go ahead and uncheck the results option and click on Archive. Now, let's go ahead and restore this archive. So let's go into the File menu, click on Restore Archive, and now we have our archive file here, which is saved as a WPBZ file. Click on the archive and then click on Open. Once you open it, ANSYS will automatically ask you where to save this file. So we're going to go ahead and save it in the same directory and click on Save. And we're going to go ahead and overwrite the existing project. So that's how you open up an archived file. So moving on to the Units menu in ANSYS Workbench, you can go ahead and select from different types of predefined unit systems such as SI, metric, or US customary. Now this checkbox here, display values as defined, means that this will use the units from the source. So let's say if you imported a CAD model, this will use the default values of the source instead of using the values in your project units. So this is where you can go ahead and change that to force ANSYS to use the values in project units or to use it from the source. The last option here is the unit system. So let's go ahead and click on that right now. Once you have that open, let's go ahead and make this box slightly bigger by dragging onto this edge and moving it to the right. So as you can see here on the left-hand side, you have a predefined set of unit systems. The column B here shows you the active project unit system. So as you can see, we've selected the number 3 metric. Column C is basically the default unit system. So every time you launch ANSYS, this will be the default unit system that ANSYS will go to, depending on which one you choose. Column D basically hides the other unit systems that you're not interested in seeing in the units menu. So let's say you want to change the default unit system to US customary. You can go ahead and click on that right there, and that will change the default to US customary. If you wanted to hide a few other unit systems, such as US engineering, you can go ahead and click on this checkbox, and now it will not show up in the unit system anymore. Now at the bottom here, you can see you can also have the options to either duplicate, delete, import, or export a unit system. So let's say we want to make our own custom system. We can go ahead and start off with a default system, say the metric system, and click on duplicate. This will duplicate the system, and you can scroll down to the bottom here, and now you'll see something called custom unit system. Now let's say we want to make this our default system. We can go ahead and check this box and check this one right here to make it into our active project and the default system. Now with this custom unit system, you can go ahead and double click on this and rename this to whatever you want. Let's call this metric 2 and hit enter. Now as you can see on the right, you have column A, which is the quantity name, and column B, which is the unit. So you can go ahead and change the default values, let's say for the angle from radian to degrees, or say change the length from meters to millimeters. Now once that's done, this will automatically save it in the project. But if you want to send this to a friend, you can go ahead and click on the export button, and this will save the unit system as an XML file. You can also import it if somebody sends you a custom unit system, and it will import it into your unit system library. Now to delete this system, it must not be active. So let's go ahead and click on number 3 and make this one the default system again. And let's click on number 20, the metric 2, and click on delete. Now once that's done, we can go ahead and click on close. So let's talk a little bit about importing CAD geometries. ANSYS has numerous geometry interfaces that are available for commercial CAD systems, such as AutoCAD, SolidWorks, and even Parasolid geometries. So all of these geometries can be easily imported into ANSYS using any type of license. However, if you want to have something called an associative geometry interface, which means that, let's say you have SolidWorks installed and you have ANSYS installed, you can go ahead and change the model in SolidWorks, and ANSYS will automatically be linked to that model and updated in ANSYS Workbench. Now for this, you might need some special licenses, so once again, you should contact your vendor regarding which geometry interface licenses you will need for your project. Now there are many different ways to import the geometry, but one of the ways is to go ahead and select cell number 3, which is called geometry, and right-click on it, and then you will see the option here to import geometry. So here's where you can go ahead and click browse, and you can browse for your different type of geometry. And if you click on this scroll menu here, you can see all the different types of compatible geometries that I can import. So I have these satfile.sat file, which is extremely common. I have IGES files, I have Parasolid, I have Solid Edge, SolidWorks, etc. So let's just click cancel for now. Now the next thing I want to mention are the properties when importing CAD geometries. So let's go ahead and click on cell number 3 geometry, right click, and click on properties to open up the properties pane window. You can also access this menu by clicking on view and then properties. The properties window will pop up here on the right side of Workbench. In order to get a better view of it, let's go ahead and close this files window. We can either close it by clicking on this X here, or once again, we can go into the view menu and click on files to hide it. So I will not be going over all of these options with you, but I will be going over the most important ones. So let's take a look at basic geometry options. As you can see here, you can filter what type of geometry you want ANSYS to import into your project. The CAD file could contain solid bodies, surface, and line bodies, So it's up to you to decide what type of geometry you need. As you can see by default, all of these three options are checked. However, this filter can be very useful at times to eliminate bodies that could cause problems during an import. Next are the parameters and attributes. An example of a parameter or attribute could be, for example, a defined dimension on the part, which is given a label or a name to it. So if these boxes are checked, ANSYS will by default import all the parameters and attributes defined in the source geometry file. But say you only want to import a specific parameter into ANSYS, here is where the parameter and attribute key come in. You can tell ANSYS to only import parameters or attributes that have this key or piece of text in it. So say we define a radius called fillet1 and another radius called ds underscore fillet1. If we leave this field blank, ANSYS will import both of these dimensions. However, if we input ds as a parameter key, ANSYS will only input ds underscore fillet1 as a parameter into ANSYS. Moving on to name selections, you can think of this as a group of surfaces or even as a specific point on a geometry that the user has given a name to. So for example, say in your CAD file you had a collection of 4 nuts and bolts, and the user created a group or named selection called bolts. ANSYS will also be able to import this type of feature. And the last option here is material properties, where if the material properties were defined in the external CAD program, they can be imported into ANSYS as well. Now, I don't want to go into so much detail on advanced geometry options. You can see here that you can also change the analysis type from 3D to 2D if you just want to do a 2D analysis. And you can also have the option to use associativity, as mentioned before. Let's say if you want to link up with an external CAD program such as SolidWorks and have real-time updates between them. And you can also import coordinate systems and many other features here, which I will not cover, but once again, you can find in the help menu. So now that we've gone over the interface, working with the units, importing a CAD geometry file, let's have a look at the final part, which is the engineering data application. So to start it up, let's begin by double-clicking on cell number 2, engineering data. So the engineering data application is where you can provide controls for all your material properties within ANSYS Workbench. So right in the center of engineering data, we can see something called outline of schematic A2. So this is where all of our materials will go for our specific project that we've created called Lifting Lug Tutorial. Now, as you can see here, there's no materials that are specified, and ANSYS asks us to click here to add a new material. Instead of making our own new material by clicking here, you can go and click on this tab called Engineering Data Sources. By clicking on this tab, you will see the whole ANSYS library of different types of materials you can use for your project. You can also think of this as a list of preset materials. So in order to get more space here, let's go and close the messages toolbox here at the bottom by clicking on this X button. So in engineering data sources, you have general materials, some nonlinear materials, explicit materials for high-speed impact dynamics, thermal materials and fluid materials, and even composite material preset libraries for you. Now by default, the general materials is selected. And once it's selected, you can see over here the outline of general materials. So this is the whole library of general materials given to you by ANSYS. So here on the left, you have the materials such as air, aluminum, alloy, concrete. And under column B, you have the option to add this to your engineering data project. So by clicking on this button, this will add this material to your project view. Now the properties box below gives you the details of the material that's selected in the outline. So let's go ahead and select aluminum alloy. And as you can see here, the properties for outline row 4, aluminum alloy, are displayed right here. So you have the density, you have the Young's modulus, you have the yield strength and the ultimate strength, etc. And to the top right here, you have the property table, and just below it, the property chart. Now these two windows give you more detail about the property that you selected here in properties of outline. So here the density is selected by default, And in the property table, you have the density, and you have another column which shows the temperature. If the temperature is not specified, then you can see in the property chart window that the default is 0. Now, let's say you want to modify a list of preset material libraries. You can go into the Engineering Data Sources view again, and under column B, you'll see this little pencil icon. Now, by checking one of these checkboxes, you can go ahead and now edit this material list. Now, if you made the changes to this material list and you want to save it, you can go into column C and click on this button here to save your materials as a new XML file, and you can send it to a colleague or for technical support. And if you want to import a list of general materials, you can go and scroll down to the bottom here and click on this button to open an existing data source from a file. Now let's add structural steel to our project. So go into the outline of general materials window, and let's scroll down till we find structural steel. So there we have it, structural steel. So we're going to click on this yellow plus sign to add it to our project. So once we've clicked on that, we can go now and click on the engineering data sources toggle to go back into our project window. And now we can see here in the outline of A2, we have structural steel now in our project. So once added, we can now choose to modify the default properties of the structural steel in this window here. So we can go and bring this up. And now you can see that all these fields in column B are editable. So let's say you want to go and edit the density, you can double click on this value and you can erase it and edit it. And let's say you wanted to change the Young's modulus, you can also change the units for each individual property. So you can click on this Pascal here drop-down menu and choose, let's say, megapascals. And then now you have it in 2e⁵ megapascals. So once again, you can double click on this and you can modify the material as you wish. Now, ANSYS doesn't include all the properties that you might need for your analysis. So that's why there's this toolbox here on the left. This toolbox gives you all the properties you could possibly need to define a material in ANSYS. So let's say for structural steel, we can go into, let's say, linear elastic properties. And as you can see, isotropic elasticity is grayed out. This means that it's already part of our material property, and we can find it right here in row 6, isotropic elasticity. Now, if let's say we wanted to add a different property and not make it isotropic but orthotropic, we can, let's say, click on this, drag it into any one of these rows and let go. As you can see, this overrides the isotropic elasticity property because now it is being defined as an orthotropic elasticity property. And this question mark means that you have to define some more parameters before continuing. So if you click on this plus sign here, you can see that now you could have all these parameters to define in each different direction for this type of property. So let's go ahead and remove this by right-clicking and deleting it. And then let's unsuppress the isotropic elasticity using this column here. So by default, if you add in a new material, ANSYS will suppress it, but we want to now unsuppress it to get it back. So let's click on that. And you can see the line is undone in this, and so that means it's unsuppressed. Let's say you had a nonlinear analysis to do. You can go back into engineering data sources, and you can, let's say, go into general nonlinear materials. And let's move this down a little bit. And you can go and choose let's say, stainless steel nonlinear material or structural steel nonlinear material. And as you can see here, it has a bilinear isotropic hardening parameter. So this is the nonlinear curve for this material. So this is a default in ANSYS again, if you're doing a nonlinear analysis. However, let's say you wanted to add something more complex and add, let's say, a multilinear stress strain curve. Well, let's go back and uncheck engineering data sources and click on structural steel. We can go now into plasticity models and choose, let's say, a multilinear isotropic hardening property and drag it into our properties outline. And now, as you can see, I'm going to bring this window up. And now we have our multilinear isotropic hardening, and it asks us to fill out this table. And this table on the right is essentially the stress strain curve for this material. So we can go and put, let's say, 0.001 and put a stress of 250, and then let's say 0.002, and let's say 255, and et cetera, et cetera. And here you can add, you can keep going until, let's say, 0.2 millimeters per millimeters, and then say 256. And then here you have your custom multilinear stress strain curve. So for this tutorial, we're not going to be using nonlinear materials, but this is just to give you an idea of how to use the toolbox. Now you may have noticed this button called Filter Engineering Data. This is just a toggle button that when selected, filters out all the material properties that are not relevant to the current study. So since we're doing a static structural analysis, you can see that all the other models are hidden. So if I uncheck this right now, you will see that it shows us all the different types of material models for any type of project. And now it added some magnetic materials and some electric material properties. And as you know, these are properties that we're not going to use in our project. So let's go ahead and keep that checked on and only have relevant properties for a project. Now getting back to the properties outline, let's go and remove this multilinear isotropic hardening property. Click on delete. And now we're back to our general structural steel material. Finally, you can also add materials by clicking on this area here where it says click to add new material. So let's say you don't want to use a default material and you want to make your own material from scratch. You can click on this and you can define something that's called new material and hit enter. And this will define a new material for you. As you can see in the properties, you have absolutely no properties here. So you would have to go and add them yourself. So let's say we go into the basic properties, you can add density, double click on it or drag it in. We can add, let's say we can enter this value as 7850. And then we can go and add a linear elastic isotropic property and drag that into the first field here. And then you can, etc. And you can make your own material this way. Now, something else that you might notice is this column B here. This could just change the color of your material. So during the analysis, if you want to show the model by color, you can use this here to define different colors to different materials. So that completes the engineering data tab. I'm just going to go and delete this new material because we will not be using it for a project, and we'll just be keeping structural steel for now. So let's click on the X button to quit out of engineering data and back into our project. So once back into our project, you can see here now the engineering data tab has a green check mark, which means it's updated. So there's a quick overview of the ANSYS interface. Let's continue to my next lesson, where we will go over building our first 3D model in Geometry Modeler.
Okay, now I'm coming to part C, that is problem solving on ANSYS workbench. Now, this is the first problem. This is a structural problem. This is a cantilever beam. And here we are interested to find out the stress deformation. And this is at one end is fixed from all sides, and another is loaded with 500 pounds. The beam is of 4-inch long, and it has a 1-inch cross section. The material properties are here. We have choose structural steel, whose Young's modulus is given, and with the help of mu n, we are able to find out the modulus of rigidity, shear modulus. It is given. So by theoretical calculation, we can find out, because it's a simple geometry, we can find out this deformation by solid mechanics relations. See, here we found this, and it says we found this. Let's try with on ANSYS to solve this. Here, how we open ANSYS. Here, these are the different modules. Mechanical, APDL, turbo grid. We are going to work on workbench. It is the latest version of ANSYS. You can also install this ANSYS from ANSYS website, and you can install a student copy of this software. It is free of cost, and it is having around 1.5 year license period. So now I am interested to do steady state static structural analysis. So here these are the different types of analysis. Now we are interested to find out to carry out static structural analysis. So by double clicking, this is a project window. Now these are the steps. These are the workflow of this ANSYS. You have to define material, you have to define geometry, then in model you have to define different boundary condition. Then after solving, you can interpret the result. So here I am creating the geometry for that cantilever beam. Somebody want to ask any question? Hello?
No, sir.
This is the design modeler. Now, how we create a geometry in this modeler? These are the different geometrical features. You can extrude here. You can revolve. You can do sweep and skin and loft. So here we want to make a sketch of that cantilever beam. So we go to sketching mode first. This is the sketching mode. Now we want to select plane where we want to draw this. So for selecting plane, we have selected the which one. Here you can see this XY plane. We have choose XY plane, and here we are making a cross section, square cross section. For extrude, the cross section should be a closed one. If it is not closed, then it make a surface model. To make a 3D model, this cross section should be closed. And you know what is happening in extrude? In extrude command, it add or delete material in a normal direction. So here we want to add the material in normal direction. Now we do this is a sketch. Now we do dimensioning here. This is a 1 meter. This is 1 meter. Okay. Now we are choosing the extrude command. You can change units here. Now selecting this sketch, apply, and now here depth. Depth is 4 meter. 4 meter. In problem, 4 meter is given. And now generate. Oh, it was not complete. So now again I have to make this sketch. Delete. Now it become solid. Earlier there was a gap, so it was not a solid. Now I have created a model, CAD model. Now going to this model, it shows tick mark, means now it is okay. Now go to the model where you have to give material properties, boundary conditions. It is taking time. Some more time, taking some more time. Okay, now we are in. So here is the geometry. This is one solid. Here the material property, we have structural steel. If you click this, you can like in videos it was told how to select material. Here we can choose different material, but as per problem we have a structural steel, so no need to change. Now mesh, we have to divide this whole geometry into small pieces. So now mesh, generate mesh. Now meshing is done. It is perfect. Otherwise you can, if you want to refine this, go to sizing. You can control the size of this. You can if you want to more number of elements, you can refine the size of this mesh size. element. Now in this we insert, we want to fix one end, so we need fixed support, and we want to give a force on another surface. So for fixed support, suppose we are selecting this, it is so simple, and here you have to select apply, it become the, and in another force we have selected this, and we have, now we want to give a force on this x size in this direction. So but so for this we not need a vector, we have to need component and in x direction here, uh, 500 pounds. So enter, this become in Newton. So we can change units here. Later on we will change. Now in solution part, we are interested to find out the deformation, total deformation, and normal stress, in a state normal stress, and again von Mises stress. Von Mises means equivalent stress, but here you can do with a lot of things. If you want find out deformation strain, you can find out various strain, stress, you can find out various stress, energy, strain energy, localized, linearized stress. These are the stress tool, many things. So depend upon the type of problem, you can select all these things. Now we did a FE formulation. FE formulation means we did a pre-processing. Now we have to solve this. So this is the icon for solving. Click here. So it is done now because you are finding right click on the here. Now this is the total deformation. This is the total deformation, unit in a meter. So this is the maximum deformation. Here it is given maximum, it is 6.7 raised to power 0.007, minimum is 0. You can also animate this, how this is happening. This is the animation of this deformation. Here this is normal stress. You can view normal stresses. This is a contour plot of this. This is the normal stresses. Maximum it is here in, because support is here na, so maximum stress is here. It is given in Pascal. You can You can make a cut section of this also by selling the cut like this. You can cut this. You can see this. You can make so many cuts. So here the total deformation, maximum total deformation, note down this 6.006 meter. If we talk in a meter, 006 meter. So come to the, and stress, normal stress is maximum is 5.3 Pascal. If you convert into that unit, now you can compare with the theoretical calculation, like in, so here PSI. If you convert this, it is nearby this, and here we find out 5.6. 5.6 means we are getting more. So there is a you can refine the now element size. You can come to this. So you, in this way you can validate. Now come to another problem. This is the heat transfer problem. This is very simple problem. This is a wall and made up of again structural steel. One side of this wall having 100 degrees Celsius and another side it is having 22 degrees Celsius. The area plate is 1 meter square and length is 0.25 meter. Thermal conductivity is 60 per meter Kelvin, Weber per meter Kelvin. Now, how you can solve this? As you know, this is a basically conduction problem, and for conduction problem, if you review the heat transfer fundamentals, the Fourier law, na? So you can find out the heat flux by using Fourier law, that is Q equal to minus K a thermal gradient. So you can do theoretical calculation also, but you can also do this thermal analysis by using ANSYS. Now I'm going to steady state thermal analysis. Here now again I am making another geometry. So I am selecting XY plane here again. Making a wall. So again going to sketching mode. Making a square. See this is complete or not. Okay, now dimensioning. vertical, one meter, 1 meter, extrude, depth is, how much it was? 0.25. Depth is 0.25. Generate. Now this become the wall. Again, now this right click is there. Edit. Again, it is taking time. Somebody want to ask question? Hello?
Yes, sir. Yes, sir. Yes, sir.
Huh?
I have one question, sir.
Yes.
If we design a composite lighting structure, so what will the process be like concrete and steel and other things?
What do? You make a two material and make a assembly of for that. ठीक है, पहले
Okay.
assembly बनाओ और फिर
ठीक है.
उसको इसमें import करोगे. तो
Okay.
यहाँ ये जो
Okay.
showing this geometry, here only the one component is there. Here if it consists of two components, तो यहाँ पे दो component. अगर एक और यहाँ पे बना देता हूँ इसमें, तो दो component बताएंगे यहाँ पे. ठीक है. तो यहाँ आप उनकी material property by clicking here, you will see the material properties here.
Hello, sir.
हाँ.
Okay.
Hello.
Hello.
So by giving material properties, and you are using composite materials, then you can take the composite property material property from the composite block from the material selection window. Yes. Somebody asking some another question.
सर फर्स्ट ऑफ ऑल थैंक यू सर. मैं ये पूछना चाह रहा था सर कि अगर एनसिस पर हमको मिलिंग करना है तो उसके लिए कैसे जाना पड़ेगा सर?
मिलिंग करना है?
जी जी.
मिलिंग के लिए एक्चुअली वो अलग कोड है उसका. मिलिंग का अलग कोड है. ये वर्क बेंच में मुश्किल होगा. उसमें हम उसमें एक जॉनसन एक एल्गोरिथम है. हाँ. है ना, by which you can simulate milling process there. Where you can calculate the life of tool.
जी.
है ना, and how मतलब how much time is it taking for doing milling operation. तो वो effective है कि नहीं. But you cannot do on this. Some other analysis is there.
So वर्क बेंच पे नहीं हो सकता वो?
हाँ, ये वर्क बेंच पे नहीं हो सकता. You can use abacus for this.
Abacus.
Okay.
Thank you. जी सर.
If you want some help, you go to online. है ना, ऑनलाइन हेल्प है, अवेलेबल है उसमें. मेरे पीजी स्टूडेंट ने किया है इस पे वर्क.
जी सर.
ठीक है, पीजी स्टूडेंट ने किया है इस पे वर्क.
हाँ.
हेलो.
हेलो.
Hello, sir.
हाँ.
Sir, I have a questions.
हाँ बोलिए।
Sir, actually, I'm an electronic student and I have a doubt, sir. What is the application of this software for electronic student?
इलेक्ट्रॉनिक स्टूडेंट लाइक यू वांट टू मेक ए जो सर्किट बोर्ड होता है ना, बोर्ड
Yes, sir. PCB. Okay,
पीसीबी
sir.
जो बोर्ड है उसकी डिजाइन कर सकते हो। सपोज जैसे जो प्रोसेसर है उसके लिए हीट एक्सचेंजर तुमको डिजाइन करना है, वो
Okay, sir.
डिजाइन कर सकते हो। ठीक है, तो यू कैन डू दोज एनालिसिस।
Okay, sir. Thank you. I got it.
ओके।
सर हेलो
यस
सर, जो आपने एंसर्स समझाया था, इट्स माय फर्स्ट टाइम दैट आई एम वाचिंग एंसर्स हाउ टू यू। सर यू हैव आपने इतने सारे प्रोसेस बता दिए, तो व्हाट इज द प्रोसेस दैट आई हैव टू स्टार्ट फ्रॉम द बिगिनर? सो
कौन सा बैकग्राउंड है, विच ब्रांच यू बिलोंग्स टू?
आई एम सर फ्रॉम मैकेनिकल इंजीनियरिंग ओनली।
Mechanical engineering. Start with the structural analysis, then go to transient analysis. Transient analysis is nothing but a dynamic analysis where you can give loads, that is time varying loads. And then
ओके
explicit analysis by, I already told you in initial that this is belongs to three level: beginning level, intermediate, and then advanced level. है ना? तो you are at the beginning level, so you try to do simple things. Okay.
यस सर, मतलब बेसिकली सर आपने बताया सिंपल थिंग के लिए। सर मुझे आपने इतने सारे स्टेप करवा दिए, तो वो
हाँ,
नोट डाउन नहीं कर पाए, तो सर कोई और मतलब जिसके थ्रू मैं एक स्टेप बाय स्टेप हम कर पाए सॉफ्टवेयर डाउनलोड करके इस प्रोसेस
आ,
को।
देखो इसमें, अगर इसमें ही जाना, देखो ये आप जाओगे इसमें,
जी सर।
ये हेल्प हेल्प मेन्यू है इसमें, ये हेल्प वर्कबेंच
ओके
हेल्प।
जी सर।
ठीक है, इट इज गोइंग टू ओपन, ये हेल्प है। ठीक है,
जी सर।
ये हेल्प है। यहाँ पे यू कैन गेट द लॉट ऑफ मटेरियल, यहाँ ट्यूटोरियल भी तुमको मिल जाएंगे। ठीक है,
जी सर।
यहाँ पे ट्यूटोरियल भी मिल जाएगी, बाकी यूट्यूब भरा पड़ा है, बहुत सारे लेक्चर्स हैं वहाँ पे, ऑनलाइन ट्यूटोरियल भी दी है काफी।
ओके
लेकिन उसके पहले ये, मतलब ये सब समझने के पहले आपको क्या करना पड़ेगा, आपकी जो मैकेनिक्स ऑफ सॉलिड है, सब्जेक्ट है,
जी सर।
वो तुमको अच्छी तरह से आनी चाहिए। ठीक
ओके
है,
सर।
और
जी जी
थोड़ी सी
सर।
आपको ड्राइंग फंडामेंटल्स है जो, क्योंकि कैड मॉडल जनरेट करना पड़ेगा आपको, तो उसके लिए आपको थोड़ा सा जो इंजीनियरिंग ड्राइंग सब्जेक्ट है, कैड मॉडलिंग है, वो तुमको अच्छी तरह से आने चाहिए। ओके।
ओके सर। जी जी सर।
और उसके बाद में थोड़ा सा आपको एफईएम भी आना चाहिए। एफईएम मतलब आपको हार्डकोर इन डेप्थ नहीं जाना है, लेकिन आपको थोड़ा समझ में आना चाहिए उस चीज को। ठीक है,
जी सर।
मैथमेटिकल मॉडलिंग में नहीं जाना है, लेकिन आपको थोड़ा सा एफईएम का समझ में आना चाहिए। तो आपको मेरे ख्याल में अच्छा आप मतलब इसके एनालिस्ट करने लायक बन जाओगे, इसको एनसिस को यूज करने के लिए अच्छे हो जाओगे।
जी जी सर। थैंक यू सर।
ओके। हाँ, आई वाज डूइंग थर्मल एनालिसिस में, लेट मी कंप्लीट दिस। ओ मैंने वो कैंसिल कर दिया इसको। So here I am inserting temperature. Here this is a 22. Apply this. हो गया. Then again insert temperature. This side I am here 100. Apply. And here I want to know total heat flux. Then solve this. So you can see the minimum heat flux is given. Maximum here, and this is the minimum. If you want temperature distribution along this, evaluate the result. Now this is the contour plot of this. This is 100 and this is so you can do various types of analysis on this. I have conducted a simple analysis. Now if you want to import, suppose अभी तक हमने क्या किया, ज्योमेट्री बनाई है. अगर आपको इंपोर्ट करना है, like if you have created CAD model in Pro-E or SolidWorks, CATIA, then how you can import the geometry inside this workbench? I'm going to tell you. Import geometry. Here this is the showing this import geometry. You want to browse this. It is working. Starting. It is taking time. मैंने क्या किया अभी तक मैंने इसके जो मॉडलर था, डिजाइन मॉडलर, उसमें ही ज्योमेट्री क्रिएट की थी. अभी मैंने ये प्रोई में क्रिएट किया है. अब मैं उसको यहाँ इंपोर्ट कर रहा हूँ. तो I have created a geometry in Pro-E. Then I saved as a IGS neutral in a neutral format. See, you are looking this. ये मैंने ये ज्योमेट्री दूसरे सॉफ्टवेयर में बना के यहाँ इंपोर्ट किया है. अब सिमिलरली आई कैन डू analysis, fix this, putting a load over here. I am giving the bone property and I can perform an aesthetic analysis Same here for this also. Okay. So thank you all. Any other question?
No, sir.
So I finished from my part. Any question? हाँ मैडम, I done है ना, I finished this. So can I leave this? अच्छा ठीक है. हेलो. हाँ हाँ ओके.
हेलो
हेलो.
हेलो
हाँ यस.
सर ये इसका कुछ पीडीएफ वगैरह या कुछ मिल जाएगा क्या सर इस सेशन का?
ये रिकॉर्ड नहीं करते क्या बाद
सर
में?
रिकॉर्डिंग है, मतलब ये वीडियो भी हो जाएगा क्या इसका?
हाँ शायद वो दे दे, रिकॉर्ड किया होगा दे देंगे.
हाँ
Otherwise,
सर वो
my email is there, brraval@gmail.com.
यस सर.
Drop me a mail, I will send you.
ओके, थैंक यू सर. थैंक यू सर.
Good evening to all. Am I audible?
Yes, yes, you are audible.
Yes, ma'am.
Okay. I'm providing you the link. All the participants are requested. Hello.
Hello.
Yes, all the participants are requested to fill up the Google form link, URL link in your chat box and submit before ending of the session.
Hello, ma'am. Where is the link?
Please wait, we provide you a link.
Can I leave now? Hello, madam. Hello.
Hello.
Can I leave now?
Rahul sir.
Can I leave now?
Where is the link? Please send the link.
Rahul sir, are you there?
I'm here. I'm here.
Hello.
I am here. Can I leave now? Hello.
Ma'am,
हाँ मैडम मैं ऑनलाइन हूँ. अच्छा हाँ, तो वही मैं कह रहा हूँ, आप ठीक है ना, यू डू दिस एंड यू दिस।
हेलो
यस मैडम।
राहुल सर।
हाँ यस आई एम। हेलो।
सर हेलो।
क्या?
सर आपका मेल एड्रेस मिल जाए जैसे कुछ कम्युनिकेट करना हो तो।
हाँ, बी आर रावल, माई नेम इज एज सॉन इन योर
ओके
बी आर
सर चैट बॉक्स में डाल देंगे क्या?
raval@gmail.com।
मैं सभी पार्टिसिपेंट्स को हम अभी व्हाट्सएप पे प्रोवाइड कर देंगे आपको सर की मेल आईडी और कांटेक्ट नंबर एंड पीपीटी आल्सो।
ओके ओके।
Yes, and I would like to thanks Dr. B. Rawal sir, who put this session on ANSYS, knowledgeable and informative. So thank you very much, sir, for that. Yes, and we are also thankful to our coordinator, sir, of TechU3 RGPV Bhopal. And I also thanks all the participants present here for exceptionally very supportive. So thank you, everyone.
Okay, madam, thank you. Thank you for
Yes.
calling.
Thank you, sir.
मैम फीडबैक फॉर्म की लिंक भी ग्रुप में देगी क्या?
यस मैं अभी चैट बॉक्स में आपको विद इन 2-3 मिनट्स में प्रोवाइड कर रहे हैं आपको।
ओके मैम।
थैंक यू राहुल सर।
ओके, थैंक यू मैडम।
यस।
Ma'am,
Ma'am, link.
Yes, I'm providing. Please check your chat box. I'm providing.
Madhurima ma'am. Hello, Madhurima ma'am. Am I audible? Sangya here.
hello. Hello. Sangya ma'am.